Hi guys, today we'll be going over computer science chapter 1 data representation, and before we do that, first we have to look at the syllabus. This is IGCSE 20 to 10, and I bet sorry, this is O level 20 to 10, and this is IGCSE 0478, and both of the syllabuses you can see, data representation, data transmission, data, and both of the syllabuses you can see here have the same topic: data representation, data transmission. And syllabus 2, this is the other one, data representation, transmission, and up until these ones exactly the same thing. So IGCSE O level, same syllabus, so we'll just close one of them. Now let's open up the topic itself, if we can find it. So the first topic, it starts with number systems, data representation 1.1, number systems. And there are only a few points here, not that much. So first point is understand how and why computers use binary. What is binary? We'll get into that. Understand denary, which is basically integer numbers. Binary, which we found out here, a term. And hexadecimal, which is another term. So three things: integer, and then binary and hexadecimal. We have to learn binary and hexadecimal. Convert between, so binary, hexadecimal, and then integer. You have to convert, let's just say, a binary number or a integer number to hexadecimal number, something like that. Then we have add two positive binary numbers and understand how and why hexadecimal is used. So a few examples on why this is used. Let's get into the notes, and we'll be again using Z Notes, a free notes website. And this is IGCSE, but O level is the same thing, same notes, so you can definitely use this video. And we'll be going over a few things in the book, and there are two books. This one is from Hodder, and this one is from Cambridge themselves, Cambridge University Press. And this is, for a lack of a better word, a trash book. Do not use this, do not study this. If you were planning to buy this, use this, just throw it away. Do not touch this. It's just bland, boring. And just use the Hodder one. So we'll go to chapter 1, and this book is much more easy to follow, easy to read. So yeah, we'll be going over this from time to time, but we'll be mainly using the notes. Now let's get into point 1. Number systems. Understand why computers use binary to represent all forms of data. So, if you think about computers, they are basically pretty dumb until you actually write your own software, write your own code. They cannot achieve anything. What they can only do is take a switch, turn it on, turn it off. So, let's just assume you have a light bulb. So a light bulb here. So a light bulb here, and it is connected to a switch. And then let's just say there is a battery here, only one terminal battery, but it does not matter. Okay, we'll draw one other terminal. So whatever. So when you close the switch, the light turns on. So the light will come out if you close it, but if the switch is open, there is no light. The computer is essentially doing the same thing. There is a switch, when it is turned on, a small amount of voltage flows through the switch, and there is an output on the other side. And when the switch is not closed, there is no voltage, and the output receives nothing. There is no voltage. So this is how computers generally on the basics work. And so computers can then only represent two things, either an on or an off state. And this is why we use binary. Binary comes from, let's just say, think about binary stars. Binary stars basically meaning two stars in a system, a pair or tandem, whatever. So binary star system, if you ever heard of that, it's similar to that. Only two values can be represented in a binary system. So it will be only be 0 and only be 1. That's it. There can only be two values, and computers only using two of these values, 0, 1, and a combination of this can do everything, I guess. So yeah, binary system, it's base 2 number system. Base 2 meaning only two values, and possible values are 0 and 1. And 0 is off and 1 represents on. A point to be noted is that the most left bit is called MSB, most significant bit. So this bit, like this is on the left side, this will be the most significant bit, the 0 on the exact very left. And yeah, basically this is called a significant bit, and bit meaning only one value, right? 1 0 or 1 or 1 singular 1, right? So this is also a bit, this is also a bit. Now what is denary number systems? Denary basically meaning base 10, or the numbers we use has values from 0 to 1, 0 to 9. So 0 1 2 3 4 5 6 7 8 9. And there, let's see, understand. So then there comes hexadecimal. Hexadecimal is base 16 number system. What does that mean? It has 16 values. It can represent 16 different values, right? So we use 10 different values to represent our calculations in humans use it. But computers can use this also and understand this also. This is particularly useful in a lot of fields, and we'll get into why hexadecimal having 16 different values is useful. And hexadecimal, you can see binary value is given for a given hexadecimal and whatnot, and denary value is also given. So let's just understand what this table represents. So denary meaning integer, so integer values going from 0 to ending to 15. So in total, 15 plus 0, which will be 16, right? 0 is also added here now. And in computer science, 0 is used quite a lot, and 0 is also considered the start of a lot of things, right? We normally count from 1 2 3 4, but computers a lot of the time will be using 0, right? 0 1 2 3 4. So yeah, if you start from 0, then you go to 1, you have counted on one place already. So 1, then if you go to 2, you have used like three numbers, right? Normally if you wanted to go to 2, you just go to 1 then go to 2, so only two numbers would be used. So yeah, keep that in mind. And students usually make this mistake a lot. They count from 0 to 15 and they say there are only 15 numbers here, but no, that will be 16 numbers, because 15 plus 0, that out of the way. So let's see hexadecimal numbers now. Hexadecimal also starts from 0 and then it goes to 9, right? After 9, denary and hexadecimal switch, right? Before that it was all the same, right? Denary and hexadecimal, so integer value, denary is integer and hexadecimal, they are the same thing. They are both up to 9. After 9, hexadecimal becomes A. So basically 10 is represented by an A, and 11 will be represented by a B, and 12 will be represented by a C. and 13 will be represented by D, and so on and so forth. So A, B, C, D, E, F, G. And it starts from 10, ends at 15. So 5 values in total: A, B, C, D, E, F. So these 5 you have to remember. After 9, if you want to represent 10, you will write A. This is a bit weird at first, but it will make a lot of sense. So let's continue and see how this will be used later. Now we have to convert between binary and denary. So let's go back to the whiteboard. Let's just say you have an integer number of 8, or we'll go one more, we'll go 9. So this is your integer number. How do you convert it to binary? So binary system works like this. You have a bunch of bits, so let's just say 0 0 1 1, then again 0 0, then again 1 1. So how many bits do you have? So 1 2 3 4. So and 4 more, so 8 bits in total. This is 8 bits, and this can represent a number. How do you represent a number? So the leftmost bit is again called the significant bit, and the rightmost bit, this one, the one will be the least significant bit. And these have a distinct value. What value? The rightmost bit, so the left one will have 128, let's just say, and the right one will have a value of 1. So most significant bit and least significant bit, and there are values in between. So let's go one by one. So first there will be 1, then 2, then 4, then 8, then 16, 32, 64, and 128. Let's add a comma. So here are 8 bits, and the value doubles. So 2, then 4, then 8, and so on and so forth. So you could even go on 256, then 5 12, then 10 24, then 20 48, then so on and so forth, 40 something something. You can go on, but no need. We'll just use up to 128 for now. And then you want to represent the number 9 in binary. So you will take the largest number you can in one go, right? So what do I mean by that? Let's just say you have 9, and 9 cannot fit into 16, right? Because 16 is definitely bigger than 9. So we'll go to 8. We'll take 8. So we'll write a 1 here, meaning that we have taken an 8. And so if we subtract 8, then 1 is left over. So we have to take 1 somehow. So we'll just put a line over under 1. So meaning, we have also taken a 1 and a 8, and the rest will just become 0, right? So we have not taken 32, we have not taken any of this, we have not taken 128. So this is what 9 looks like in 8-bit binary. So as you can see, these are one just 0 0 0. You can just even slice them off, right? You can just write 0 0 1. This will be 9, right? Why? Because this place represents a 1. So 1, this place represents a 2, but we do not have to, as this is a 0, and we do not have a 4, right? Because this will be the 4 value. We do not have a 4. We only have a 8. So 8 plus 1 equals to 9. So this is how you convert a number to binary. Write out the values of each bit. So starting from 1 and ending at 128. Then you take the largest possible number. So let's just say we had the 35. We wanted to represent 35. What is the largest number we can take and subtract from 35? 32. So 32 will be subtracted. Then we have left over 3. So we put a 1 over here. We have left over 3. Again, we can subtract something from 3. What can we subtract? let's just say largest number is 2. We'll just subtract 2. Put a 1 here, and then there will be 1 remaining. So put a 1 here. Boom. And rest will be 0, 0, 0. This is how you write 35 in binary. So binary calculations are pretty straightforward, taking an integer binary number into binary. And now converting back, right? If you think about converting back the numbers, what will you do? Let's just say you have been given a number, I don't know, 0, 0, 1, 0, 0, 5, then 6, 7, and then 8. Let's just say this is the number you are given. Just write out the values. So 1, then 2, then 4, then 8, 16, 32, 128. Acha, we forgot 64. So 64 will be in between this. So how many numbers do you have? We have this one, and this will represent what? A 1. So we have a 1, then add. Is there a 2? No, we do not have a 2 as this is a 0. We have a 4. So add a 4 here. Add that 4, then this one is a 8. We do not have 8. This one is 16. We do not have 16. We have 32. We have 32 and the rest are 0, so we do not need to take that into account. So 32. That is 5 plus 32 or whatever. So 37 would be the final answer into integer. So integer numbers converted into binary, right? We have learned that. Now binary numbers converted back into integer. Now converting into hexadecimal is our next goal. How do we convert a number into hex, or hexadecimal is commonly known as hex? So if I use the term hex from here on out, just remember I am referring to hexadecimal. So let's see how they are saying to convert to hex. Separate each value from each other, convert them to denary. Each separate denary value converted back into binary. So converting hexadecimal to binary. Okay, hexadecimal into directly binary. Okay, no problem. We can do that. First, sorry, so we have to first look at what hexadecimal is. Hexadecimal will go like this. So 1, then 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, then A, then B, C, D, E, F. Total 16 values in hexadecimal. And then we have to convert a number into hexadecimal. Let's just write out 32. We have to convert this into hexadecimal. How do we do this? So easiest method I could use, or the usual method I use is basically this one of 16 to the power of something. So let's just use that for 16 to the power of something. So if we have 32, we will need to subtract again. Like uh, we have seen at binary numbers, and we just take a number, then subtract the largest number we can possibly get. Right? So yeah, let's just think of the largest number we can subtract, and the largest possible number will probably be 32. And how can we know the largest possible number will be 32? We do not have 32 here. So this is where the dilemma is. This is where you need to understand how this one works. So hexadecimal numbers come out as like 1 2 D3 or F3 9A, something like this. And again, we have four places, let's just say four distinct values, right? And like binary, these places, right? These places from left to rightwards, right? Going from left to rightwards, hold an integer value or equivalent. And this basically is 16 to the power of 0, then 16 to the power of 1, then 16 to the power of 2, then 16 to the power of 3, something like this. So 16 to the power of 0 is basically 1, 16 to the power of 1 is just 16, and 16 to the power of 2 will be something you have to multiply and find out. So let's just do it here. 16 times 16, and then we'll get 36. So 3 carry over, 6 1 is 6, 7 8 9, then 0 6 1. So 6, then if we add a 0 here, we have 1 carry over, and then 5 and 256. 256. We'll just convert 3. 16 to the power 3 is very big, so we'll leave it out. So we have these three values, 256, comma 16, comma 1. And then we have to look at 33. Can we subtract 256? Nope, we cannot. Can we subtract 16? We can. How many? 2 times. So we have 16 into 2. And then what? Can we take 1? No. So 1 into 0, then 256 into 0. These are 0. And then we have to write the number out. So as we have 4 digits here, the leading one, 16 to the power 3, it will be 0. So we start off with 0. Then 16 to the power of 2. Did we use that? Nope. So we have to give a 0 again. We did not use that one. Then 16 to the power of 1. So 16 itself, did we use it? Yeah, we used it 2 times. So we write 2. And did we use 1? No. So again, so 0 0 2 0. This is a bit complicated, I know, but I think this is the easier method. Though here there is another way to convert, I think. They might show. You can just read the notes and try to find out if there is another way. They just divided by 2, divided by 2, and then convert direct to binary and whatnot. I think this is more complicated than my method. Um, let's do this once more, and I think this will make more sense. So imagine a number. Let's just say 192. And then we have our number that would be 16, comma 256. 256 will again not be used. We can already know that. And these represent 16 to the power of 2, 16 to the power of 1, 16 to the power of 0. And again, why 16? Why 16 to the power of something? Because hexadecimal works with only 16 values, right? 16 values, so 16 different places. So the base will be 16 and the exponent or the power, it can go up to 2, then 3, then 4, and so on and so on. So let's convert this. What is the largest number we can subtract? 256 we cannot. So a multiple of 16 will be used. So you'll just write 16 here and then keep on multiplying a number. So let's take an educated guess. What number can we multiply 16 with? So we get close to 92. What number? So if we multiply 10, 160, right? That's not it. We have to go higher. If we take 5, 5 will not also work. Sorry, why am I even taking 5? We have taken 10. It did not work. So something more than 10. 160, then 120. So I think somewhere around, I don't know, 15, 14 will work. So let's just see if 15 works. So 5 ones are 5, 6, 7, carry was 3. 5 6 are 30, carry 3. 5 ones are 5, 6, 7, 8. So 80, then 0, then 6, 1. So as we can see, it went much over 200 and whatnot. We need to go 192. So let's go with 13. Let's just go with 13. 3 6 are 18. So 4 0 6 1 8 and then 0 and then 2. So this one again also went over. So we have made two pretty bad educated guesses, but it does not matter. We can multiply once more. So 12 will surely do it. And 16 to the, or multiplied by 12 will be 2, then 2, then 6, then sorry 0 1. Yep. So 0, sorry 2, then 6 7 8. Did I do something wrong here? We just let's quickly pull out calculator. The 16 into 12, I think 192. Yeah, I think I made a mistake. Let's do this calculation again. And a 16 12, 2 6 are 12, so 2 ones are 2 3. Yeah, I made this mistake here. So 32, then 0, then 116 will be just 16. So now we have exactly 192. And how many 16s did we use? We used 12. So the first digit, let's just say we want a 3-digit number in hexadecimal. So the first digit will be 0, as we did not use any 265. Did we use 16? Yes, 12 16s were used. How do we write this into hexadecimal? We cannot just write 12. So we know that hexadecimal is similar to integer up to 9. Then it goes 10. 10 is A. 11 is B. And 12 is C. So we have to use C. So 0, C, 0. And so on. So if the number goes on and on, if we use a 1, we'll just write a 1. Let's just say if we ever use 256, write a 1 here. If we use a lot of 256s, then we have to write A, because we use 10 256s. And then you can start to see why this matters. Only using 3 digits, right? Only using 3 digits, we can represent, up to 25600, no, sorry, 2560, and then you can also include a bunch of 16s. How many can we include? So f is like equal to 15, right? So the number f, it basically means 15 into 256, then plus 15 into 16 plus 1 into 16. So imagine how large this would be. So only by using 3 digits, we can represent such a large number. So this is why hexadecimal is useful. A lot of information can be crammed into a small area, or a small footprint, sorry. And this is how hexadecimal works. And hexadecimal can be converted directly to binary. I repeat, hexadecimal can be converted directly to binary. You do not need to take the hexadecimal. Let us say this is the number you are given in hexadecimal, and they say convert this into integer. You have to multiply all this and add them up. This is very, very tiring. So how do we convert this directly into binary? One hexadecimal number will be converted to 4 bits of binary. So this f, it will be basically 1111. Why? Because this f represents uh, a 16, let's just say. So let's see, 111, what does this 111 represent? It will be 1 plus 2 plus 4 plus 8. So this f represents 15, and we can add these all together. We'll get what? If we add 2 and 8, it is 10. 1 and 4 will be 5. So it comes out to 15. And I made a mistake here. It will only be highest 15. So f represents 15. And so if we write it in 4 bits, it will also come out to 15. And this will also be 1111, and this will also be 1111, right? So you just have to take all this and write it together. This is your answer in from hexadecimal to binary. And any other number, let's just say 93A, convert this into binary. A will be 10. So I think this will be, sorry, let's erase this. This will be 1. So 8, and then a 0, because we do not need a 4. We need a 2, and then 0. So 8 plus 2, 10. This one becomes this, and we need 3. So 1, 1, as this will be 1 and this will be 2. So 3, then 0, 0. And then 9 will basically be 8 plus 1. So 1, then 0, 0, 1. So this will be an answer in binary. Very easy. Just take one of these numbers and it will come out to 4 bits. And just take one and convert it to binary. Take this one, convert it into binary. Take this one, convert it into binary. And this is how you just convert between binary and hexadecimal directly. If they say take a hexadecimal number, convert it into integer, actual integer numbers, then you have to multiply and see which one is what, and yeah, it becomes pretty hard. Here they did the same thing. This is the hexadecimal number given. They took the integer number and 4 bits of binary, 4 bits of binary, 4 bits of binary, plus d is 13 and 4 bits of binary, f is 15, 4 bits of binary, and then the final answer you just add it, without any gaps, just write the whole thing. Converting binary to hexadecimal. And if you convert binary back directly back to hexadecimal, You just take the binary value, divide it up to 4, then again 4, again 4, just divide it up and add 0 0 here because only 2 bits were here, so make it 4 bits. Then the binary value or integer value will come out, and just take 13, directly convert it into D, take 15, convert it into F. Converting the value of binary as shown above, and then convert the final answer. So you can read this if you want. Now, binary calculations, adding and subtracting. We have to follow this pattern. So if we add a binary 0 to a binary 0, we get 0. If we add 1 and 0 and 0 and 1, we get both cases 1. If we add 1 and 1, we get 0 and carry 1. If we get 3 ones at the same time, we get the answer 1, and then we have to carry 1 over. Let's see how this actually works out. So adding the number 0 1 0 1 to the number 1 0 1 1, right? Let's just say add 1 and 1. From the table we can see this will produce a 0 and 1 will be carried over. So again 1 and 1, this will produce a 0 and 1 will be carried over. So this will again produce a 0 and then 1 will be carried over, and then there's also a 0, then 1 will again be carried over. So where will you write this one? Do you write it here? You cannot. Why? Because you have added 4 to a 4-bit number to a 4-bit number, and a 5th bit is generated. This is what they call an overflow error. When adding two values, if the solution exceeds the limit of the given values. Example, the solution has 9 bits, but the question has 8 bits per value. The 9-bit is called overflow. So this indicates that the memory doesn't have enough space to store the answer to the addition done in the previous part. And here they added and the overflow is generated. But it does not matter, just remember, if an extra bit is generated during addition, this is called an overflow error. And again, if 3 ones are added, so let's just say 0 1 and then 0 1, then 0 1, then 1 1. We add this, right? Let's see what happens. We'll get a 0 1 and we will get a 0, and there is triple 1 here, so we get the answer 1, and 1 is also carried over, and then we get 1. So by adding these two numbers, we get 1 1 0 0. Triple ones add up to a 1. 0 and 1, any kind of 0 and 1 addition will always result in only 1, and if there is a double 1, it will result in 0 1 carryover. Just remember that, pretty easy, and you will get the hang of it pretty fast. Sorry for switching between light mode and dark mode over and over, but nothing to do. Now let's see. I think that was all for this chapter. Binary calculations, overflow. Yep. So uses for hexadecimal we did not see yet. Let's see if there is a use for hexadecimal. Yeah, so uses of hexadecimal. So the syllabus gives us here. Understand why hexadecimal is used as a beneficial method. So the question might sometimes ask you, What is a common use of hexadecimal numbers? So you just have to memorize this and give out the answer. It is used to represent colors in HTML. So you just write it is represent used to represent colors in HTML. It is used to represent MAC addresses, media access control. You do not need to write the full thing, just write MAC addresses. Remember these ones, and it is used in assembly language, it is used in memory dumps, it is used in debugging, it is used in IPv6. So these are the few examples. What are memory dumps given here? What are assembly language given here? Pause and read if you like. So two 8-bit binary numbers. I think I only showed you how to add two 4-bit numbers, but 8-bit, same thing. Understand the concept or overflow and why it occurs in binary addition. So as you know, like if you try to add two big numbers, you cannot represent that in 8-bit, let's just say 8 bits or 4 bits as we have shown. Then an extra bit is needed, and this is called an overflow error. For an 8-bit value, if the value is greater than 255, the overflow will occur. And yeah, this is all for chapter 1.1, number systems. We will Okay, 1.1 number system continued. So this one is also under number system. So let's also see what this is. 5 and 6, two things. Perform a logical binary shift on a positive 8-bit binary integer and understand the effect it has on the positive binary integer. Logical left and logical right shift and multiple shift. And then bits are lost. Positive binary integer multiplied or divided according to, okay, blah blah blah, and there is 2's complement. So what is a shift? Let's just say there is a given binary number 0 1 1, and they say perform a logical left shift of one step or something, right? Logical left shift of one step. You just move the numbers to the left side. Let's see what happens. So if you move the 0 to a left side, this 0 will be thrown away. Why? Because there is no more bits left. We have a 4-bit number. 0 will be thrown away. So the 0 will come one step here. The 1 is thrown away. Then the 1 will come to the 0 place. And this one will come to this place. So, and there is one empty place left over. Leftover place will add a 0 here. And if the number was bigger, let's just say there was 1 0 1 0 and 0 0 here, what will happen? So the 1 will move over here. So 0 1, and basically this 0 will be thrown out and the whole number will be shifted to the left one side. So 1 0 is thrown over. Let's just cut this one and just write the whole number first. So 0 1 0 1 1 and then 0 0. So original number was 4 and then 3 bits. So 7 bits long. Now 7 bits long. No, sorry, it was 8 bits long, including this 0, which it threw away. So original number was 8 bits long, and we only now have 7 bits, as 1 0 is thrown over, right? Because we moved the numbers, every number was moved one side to the left. And so we need to make this 8 bits again. We just add a 0. What happens when you move a number to the left, right? Logical left shift. The number it represents, right? The integer number, let's just say the integer number represent here was 52 before, right? Before this was 52. After you shift it one side to the left, the number will get multiplied by 2. So you'll get 1 or 4. After one logical left shift is performed, only moving one step to the left. If we move one bit, right? If we take one bit, we move it to the left and we move it again. So two places left shift, right? Two places logical left shift. The number gets multiplied by 2 and multiplied by 2 again. So basically multiplied by 4. So if we go to the left side, it will be multiply. If we go to the right side, it will be division. So take the numbers, we have gone to the left once, we need to go to the right again. So just take the rightmost bit, throw it out, move the numbers or the remaining numbers, just copy them over, and then just add a 0 at the end. That's basically it. Logical left shift and logical right shift. You can go 3 places at once, 4 places, anything the question tells you, right? If they say 4 places, take 4 bits, throw them out, copy the remaining number over, add the bits to the end, add the zeros to the end. Boom, done. So this is how logical shifts are done. Now, what is a 2's complement? Basically, a 2's complement is a way to represent negative numbers. Okay, computers now, up until now, you have only seen them store positive numbers with integer, binary, hexadecimal, and then binary numbers. Only positive. How do we store negative numbers? We can store negative numbers in binary by using the 2's complement method. This basically works out to 0 1 0 1 1 1 0 1. So this is my 8-bit number. I need to convert this to negative. This was positive, right? I need to convert this to negative. And this 8-bit number, right? This represents a denary or integer value. This is called an unsigned 8-bit number. Unsigned. There is no sign here. And if we convert this to a negative number, it will be a signed 2's complement 8-bit number. Okay, what does that mean and how does that even happen? Take this number, flip the bits, add 1. Take this number, flip every bit. So 0 becomes 1, 1 becomes 0, 0 becomes 1, triple 0, so triple 1 I mean, so triple 0 will be added, then 1, then again 0. Flip the bits, then add 1. So this will be our final result. This is a signed 2's complement, and whatever number was here is now in negative form. So what number did we originally have? We had 1, and then we had 4, 8, 16, 64. Let's just say we had positive 74, right? Okay, no need to assume. Let's just calculate this out. I just do not have a calculator on hand, so this will be a bit time consuming. Let's open this up. We have 1 plus 4 plus plus 8, then plus 16. Okay, then 64. We had 93, right? We have 93. This is a positive number. Now in negative, after doing the 2's complement, right? Flip the bits, add 1. This is how you do 2's complement. The number becomes basically the values, right? These values all stay the same. Only the first bit or the most significant bit becomes a negative value. So negative 128. It was positive before. So now we have to add all the numbers. Like before, we took these numbers, we added them up, and it came out to 63. We have to take every number, add it up. So first number becomes negative 128. Then we have to add it to 32. Then 0, 0, 0. Then we have 2. Then we have 1. So negative 128 plus 32 plus 2. So basically all the values left over here. Let's add them up. So 1 minus 120, 128 plus 32 plus 2 plus 1 minus 39. As you can see, we took 39 and it just became minus 39. This is how you represent minus number or negative number into its complement. Flip the bits, add 1. Take a binary number, okay, binary 39. If you want to write negative 39, plus first write a binary number, positive binary number for it. Flip the bits, add 1 to the end, add 1 to the end, add a positive binary 1 to the end. And then this number has become negative. So this is 2's complement. It is used to represent negative numbers. Let's see if we can take a quiz, deep dive quiz. Let's see. So complete the sentence. Memory dumps of current RAM contents are often displayed in dash format to make it appear in a more visually compact form on the screen for easier human reading and transcribing. So I think the answer should be hexadecimal. We'll just write hex. Let's see if it is accepted or not. The answer is hexadecimal or hex, as you can see. Next question. So this is a question from the later chapters. We haven't done it, so we'll just select one. I guess we got it right by mistake. So now I think we can do this one. What will occur if unsigned integers this and this are added together when only a nibble is reserved in memory to store the result? A nibble basically means 4 bits, and if we add these together, an overflow will occur. So overflow, I think overflow will be the answer. Overflow is the answer. A nibble is 4 bits. If you add this to this, the last bit, as you can see, 1 and 1, it will evaluate to a 0, then 1 will be carried over. So an overflow error will occur. Convert this into 8 bits without spaces. So hexadecimal number is given, converted this to binary. One hexadecimal value will be 4 binary bits. So A is 10, if you remember. How do we write 10? 1, 0, 1, 0. The first one from the left side is 8. Then comes 4. 4 is 0. We do not need a 4. Then comes 2. We need a 2 because 8 plus 2 is 10. And then 0 because we do not need a 1. And then we have to represent 2 in 4 bits. 0, 0, 1, 0. So this will be the answer. Here is the definition given. You can check if you want. Now comes logical shift. Apply a logical shift left of 2 places on the byte. This 2 places to the left side. So whatever number is given, throw out the left 2 bits and add them to the back. So if we throw left 2 bits out, what will happen? This will be the start of the number, right? 1 0 1 1 1 0. So let's see if we get any number with this at the start. So this is the start we are looking for: 1 0 1 1 1, then 0, then two zeros are added at the back. This will be the correct answer. Here's why, and you can rate this if you want. This is again from something we did not read. We'll just select something and move on. Convert this into denary. This will take a bit of fumbling and we have to bring out the calculator. No matter, no matter. Let's actually do it. My bad. Opened up the browser by mistake. So let's take the calculator. C7, right? C7. This basically means the 7 is 16 to the power 0 position. C is 16 to the power 1 position. 16 to the power 1 position is basically 16 into C will be, let's just see, A, B, C. A is 10, right? So 10, 11, 12. We have 12 into 16, 192. And then 7 we have to add. Why? Because 16 to the power 0, the position here, the 7 is 16 to the power 0 position. So 16 to the power 0 is 1, right? And 1 into 7 is 7. So my bad, we have to add 7, 199. So 199 is the answer. Submit. Here's why. That was the quiz, and that was all on chapter 1.2. Next we'll be covering chapter 1.2 next. And yeah, that covers everything. I guess that will be all for today. So yeah, goodbye.